If you ask me which of the two rivers is the squiggliest, the answer is easy, the top one. But if you ask me which is the squiggliest river on Earth, that's where things get tricky. Let's dive deeper. This map shows almost all the rivers on our planet. I got this data from the HydroRIVERS database, link is in the description. However, if I plot every data point, I actually get this. So why is the whole world covered in rivers? As far as I know, the Sahara or Greenland aren't exactly filled with rivers. Well, you see, this dataset doesn't actually show real rivers. Instead, it shows potential river networks based on digital elevation data, meaning it maps where water could theoretically flow just based on the terrain and slope. But to make the map more realistic, we can filter out the smaller segments using a metric called discharge. This is basically an estimate of how much water would flow through each river if there were any water. And in this map, I only show segments where discharge is greater than 10 cubic meters per second. This is still not perfect, but it's much better. But how do I go from this to individual rivers? Well, there is another problem. This dataset is purely hydrological and it doesn't include any river names. Also, since rivers are split into smaller segments and connected to many tributaries, there is no easy way to tell which pieces belong to the mainstream of, let's say, the Mississippi. I could give it a go, but thankfully I know another source that does contain river names. OpenStreetMap. However, because OpenStreetMap is more built for streets rather than rivers, I decided to focus on urban rivers. Rivers that flow through big cities like the Thames, Seine or Hudson. And although I got some nice maps, this still didn't feel right. Some rivers were disconnected, others were incomplete, and the scaling was all over the place from city to city. Also, yes, OpenStreetMap has river names, but they are not always consistent. For example, Danube is called Donau in Austria, Duna in Budapest, Dunav in Serbia, and so on. Just before I was about to give up on this project, however, I found this dataset containing 687 major rivers with their names and coordinates. So now, finally, it's time to measure squiggliness. But how? Well, one way is to measure sinuosity, that is, measure the length of the river and divide it by the distance between the start and the end point of the river. The higher the sinuosity, the more curvy a river theoretically is, but we have to exclude some outliers like the Huaihe River in China, which has a high sinuosity because of those loops here, which are actually lakes. So after filtering out the outliers, the river with the highest sinuosity is the Konokawa River in Japan, with its actual length being almost 5 times the straight line distance between its start and end point. Second on the list is the Brandas River in Indonesia, followed by the Grande River in Bolivia. But those rivers don't feel squiggly, they just bend a lot. Sinuosity only tells me how far a river strays from a straight line, not how often it twists. So I needed another metric. This time I measured the average turning angle per unit of distance. The more frequent and sharper the turns, the higher the value, and the more twisty and squiggly the river is. So, after measuring this, the squiggliest river is the Chi River in Thailand, followed by Rio Lemba and Rio Ulua, both in Central America. And indeed, those rivers look very squiggly. But this is wrong. You see, as always, after checking the top results, I also look at the bottom, the least squiggly rivers. And down there we have rivers like Copper Creek and Diamantina, both in Australia, and they look suspiciously straight. Indeed, if I plot the actual geometries I have for those rivers in Google Earth, the resolution is very low. These rivers do have bends, but they are not being captured because the data is just too sparse. In fact, if I plot the average turning angle against the average sampling distance for all rivers on a log-log scale, I get a straight line. That means that the squiggliest rivers are just the ones with more frequent data points. So my whole analysis is wrong. Okay, I give up. I don't care. I don't care. I just wait the rest. I mean, what the hell? Oh, all right. It's not that bad. Yes, rivers on the lower end are definitely not represented accurately. But it could be that rivers with more frequent data points have that resolution because they change direction more often. Do you get what I mean? I hope you do because I'm getting slightly mad. I'm having a look at Rio Lemba, and although the geometry doesn't match the river perfectly, the resolution is at least good enough to capture most of the turns. Another way to look at this is to find the rivers that deviate the most from the fitted line. In other words, rivers whose average turning angle is higher than what their resolution would suggest. And a river that deviates from the fitted line but also has high average angle is Rio Paraguay, which looks squiggly, I guess. However, not very far from here, I accidentally discovered another river, and this one looks even squigglier. This is the Bermejo River. It wasn't in my dataset though because it's a smaller river. And that's the thing, smaller rivers are bound to be twistier, especially ones in hilly terrains, as they tend to follow the natural curves of the land more closely. And I bet there are tens of thousands of them around the world. Could I even stand a chance at finding the squiggliest one? I'm not sure if a truly comprehensive dataset even exists, and if it does, I doubt if it's accurate enough. I gave it a go with what I could find, and you could say that I failed. Yeah, maybe you don't really fail as long as you learn something along the way. And one thing I definitely learned is that I should never work with river data again. I hate rivers. Goodbye.